In this video, we're going to explore the shapes of molecules. The Lewis structures that we've been working on allow us to tell what the shape of a molecule is going to be around a central atom. So far, we've been thinking of molecules and writing them as simply two-dimensional structures. And so, the way that we've been drawing CH4, for example, would seem to imply that we have a 90-degree angle between this hydrogen, carbon, and hydrogen. However, experimental evidence does show us that that bond is actually 109.5 degrees. And so if we add up all four of those angles, at 109 degrees comes out to 438 degrees, which is impossible, as there are only 360 degrees in a circle. And so the sum of these angles tell us that the methane molecule must be three-dimensional, and not simply the 2D representation that we draw. And so it turns out that the actual shape of methane would look something like this. In this case, this is carbon tetrachloride, but it has the same molecular shape that methane would. When we use this sort of notation with our three dimensions, the way that we will view it is any lines that are simply straight, solid lines like these, we consider to be in the plane of whatever medium we're looking at. And so we can think of it as this chlorine, carbon, and chlorine are all in the same exact plane, while this chlorine, drawn with a wedge, would be coming out at us, and this chlorine here, drawn with a dash, is going back behind, back into the board, or into your screen. Now that we have a basis of thinking of molecules and representing them in three dimensions, we're going to look at how we can actually predict the molecular shape of molecules. Valence electrons, or electrons in general, remember, will repel one another. And so molecules will adopt a three-dimensional geometry that helps to minimize that repulsion. In other words, the electrons will look to get as far away from each other as they can. The theory that allows us to use this idea in order to predict the shape of molecules is known as valence shell electron pair repulsion, or the Vsepr theory. Vsepr basically states that the shape of a molecule can be described in the terms of the distribution of bonding atoms around the central atom. That leads us to what we call the molecular geometry. The molecular geometry of a compound refers to the shape of the compound in reference to where all of the atoms are located. This is different from the electron pair geometry, which describes to us the geometry of the compound in terms of all of the different electron pairs. In order to use Vsepr, we have to identify what we call electron domains. An electron domain is simply a region where we expect to find electrons. Those can be either bonding pairs or non-bonding pairs. In looking at electron domains, we consider one area where we find electrons to be one domain. In other words, a single, double, or triple bond would all be representative still of just one domain. And so electron domains, as I said, are simply regions where we find electrons. So for instance, when we were looking at methane earlier, the Lewis structure of methane looks like this. And we find 1, 2, 3, 4 areas around the central atom that have electrons. 4 electron domains. Likewise, if we look at the Lewis structure of water, this is where we have to be sure that we're drawing our lone pairs on our Lewis structures. We look around our central atom of oxygen, and we also find 1, 2, 3, 4 electron domains. Later on, we'll talk about how we distinguish the difference in shape if all of those domains are bonding or non-bonding pairs. To look at one more example, the Lewis structure of carbon dioxide looks like this. And when we count the electron domains around our central carbon atom, we find 1, 2 areas where we find electrons. And so 2 electron domains around carbon in carbon dioxide. And so again, we have 2 different geometries that we will identify when using Vsepr theory. We have the electron domain geometry, which will be the arrangement of the electron pairs in space, and the molecular geometry, which refers to the arrangement of the atoms in space. Sometimes those will be the same. Some molecules will have the same electron domain geometry as they do molecular geometries. However, when some of those domains are lone pairs, then the molecule will have a different molecular geometry than the electron domain geometry. And we'll take a look at what that means in a bit. Let's begin by looking at the simplest electron domain geometry. If we only have 2 groups around our central atom, both of those groups have to be bonding groups. We can't have any lone pairs. Our electron geometry is what we call linear. The molecular geometry is also linear. And the bond angles are going to be 180 degrees. We can see the example here of carbon disulfide, in which we have a central carbon atom, 2 sulfur atoms. You can see we have 1, 2 electron domains. And so the electron domain geometry is equal to the molecular geometry. Another example would be carbon dioxide that we looked at earlier. We can see that we have 2 electron domains around carbon. So it has a linear electron domain geometry. And since both of those domains are bonding groups, neither are lone pairs, that means it also has a linear molecular geometry. In the next set we're going to look at, we now have 3 electron groups around our central atom. This gives us what we call a trigonal-planar electron domain geometry. If you're thinking in 3 dimensions, think of a fidget spinner. A fidget spinner would have a geometry very similar to what we consider to be trigonal-planar. In this example of boron trichloride, the boron would represent where you hold the spinner, and the chlorines would be the outside. You would hold it in the center and spin it, and all atoms are in the same plane. So a trigonal-planar electron domain geometry. In the case of boron trichloride, none of those 3 electron domains are lone pairs, and so it is also a trigonal-planar molecular geometry. And we get bond angles here of 120 degrees. Boron compounds will quite often have a trigonal-planar molecular geometry because boron tends to form 3 different bonds. Boron trifluoride would be another perfect example. We've got 1, 2, 3 electron domain geometries. All 3 of those are bonding, and so we have a trigonal-planar electron domain and molecular geometry. If we have 3 electron domains, and only 2 of those are involved in bonding, however, with 1 lone pair, we now have a molecular geometry which we identify as bent. And so in the case of sulfur dioxide here, we've got 1, 2, 3 electron domains around our central atom, making it a trigonal-planar electron domain geometry. However, only 2 of those are bonding electrons. One of those is the domain of a non-bonding lone pair. And so the actual molecular geometry, when we consider just the atoms, is what we call bent. And the bond angles will be somewhere less than 120 degrees. Now we look to add in yet another electron domain. So now we're talking about molecules that have 4 electron domains around the central atom. We call this electron geometry tetrahedral. A perfect example of that is methane that we were looking at earlier, or something like the carbon tetrachloride. And so if all 4 of those electron domains are bonding with no lone pairs, the molecular geometry is also tetrahedral, and we get bond angles of 109.5 degrees. And so remember that the solid lines represent atoms or domains that are in the same plane, whereas the dashed line and wedge lines represent atoms that are going out at you, as in the case of the wedge, or back behind the screen in the case of the dash. If one of our bonding groups is a lone pair and only 3 are bonding, we call that a trigonal pyramidal molecular geometry. Here we have phosphine, pH 3, and so we can see that we've got 1, 2, 3, 4 electron domains, so an electron domain geometry of tetrahedral. However, only 1, 2, 3 of those domains are bonding. 1 is a non-bonding lone pair, and so we have a trigonal pyramidal shape, where now the bond angles will be somewhat less than 109.5. Another good example of a trigonal pyramidal compound is going to be ammonia. Ammonia has a formula of NH3. When we do the Lewis structure, we find 1 lone pair on our nitrogen. And so again, we have 1, 2, 3, 4 electron domains for an electron geometry of tetrahedral. However, 1, 2, 3 of those are bonding, 1 is non-bonding, and so the molecular geometry of this is going to be trigonal pyramidal. Now, if we have 4 electron domains, but only 2 of those are bonding, and 2 are lone pairs, again, we'll have a tetrahedral electron geometry because we have 4 electron domains, but the molecular geometry when we have 2 lone pairs on the central atom is going to be bent, as in the case here of SH2. 1, 2, 3, 4 electron domains, but 2 of those are non-bonding. And so the shape of the molecule is going to look like this. Another example of a bent molecule with an electron domain geometry of tetrahedral is going to be water. There's our Lewis structure for H2O. 1, 2, 3, 4 electron domains for a tetrahedral electron domain geometry, but 1, 2 of those are bonding, 2 are non-bonding lone pairs, and so we end up with a bent molecular geometry with angles that are less than 109.5 and even less than they would be in a trigonal pyramidal coordination. And so we can see that pattern continuing. Here we have 5 electron domains, which will be a trigonal bipyramidal electron domain geometry. And so if all 5 of those are bonding, none are lone pairs, then the molecular geometry is also trigonal bipyramidal. Now here, once we start getting to the trigonal bipyramidal and beyond, we have to identify a couple of different regions around the central atom. Here we have axial positions above and below the atom, and we would consider these 3 to be in equatorial positions. And so if you were to hold this molecule between your fingers, maybe your index finger holding here and your thumb holding here, then these 3 would be spinning in between, all in the same plane. If one of the electron domains in a trigonal bipyramidal is a lone pair, then we have what we call a seesaw molecular geometry, as we can see here with sulfur tetrafluoride. 1, 2, 3, 4, 5 electron domains for a trigonal bipyramidal electron geometry, but one lone pair, and so we have a seesaw molecular geometry, and so on. If we have two lone pairs, we have what we call a T-shaped molecular geometry, and three lone pairs, as in the case of xenon difluoride, our molecular geometry is actually back to linear. Trigonal Here's an example of the PCl5 with the trigonal bipyramidal shape, which helps us to illustrate the three dimensions of this compound. So like I was saying earlier, these two atoms represent our axial positions, and these three represent our equatorial position. And so if you were to hold the molecule by this atom and this atom, these three would spin in the middle. And so this is, again, an example of a trigonal bipyramidal electron pair geometry and trigonal bipyramidal molecular geometry. Here we can see a little better the three dimensions of sulfur tetrafluoride. And so we can see again 1, 2, 3, 4, 5 electron domains for a trigonal bipyramidal electron domain geometry. But one of those domains is a lone pair for a seesaw molecular geometry. And we can see where that gets its name. If these are the base of the molecule here, then you can picture, if this was on its side, a couple of kids on each end here riding a seesaw. And finally, we come to our last electron domain geometry with 6 electron domains for an octahedral electron geometry. If all 6 of those are bonding groups with no lone pairs, it's also an octahedral molecular geometry. And we have bond angles of roughly 90 degrees. And so in the case here of sulfur hexafluoride, 1, 2, 3, 4, 5, 6 electron domains, all 6 of those are bonding. We again have axial and equatorial positions. We have axial atoms here, and then equatorial along the middle. If in an octahedral electron geometry, one of those domains is a lone pair, we have what we call a square pyramidal molecular geometry, as in the case of bromine pentafluoride. Lastly, if 2 of those domains are lone pairs, we have a square planar molecular geometry, as we see here with xenon tetrafluoride. So again, if we're thinking axial and equatorial positions, all of the actual atoms around xenon are in the equatorial position, and what we're not able to actually see here would be the lone pairs, which would be here and here in our axial positions. So here's a good 3-dimensional representation of our sulfur hexafluoride. And we can see our axial atoms here and our equatorial atoms all in a plane in the center for a classic octahedral molecular domain geometry. And so, when you're using Vsepr in order to predict the shape of a molecule or ion, the first step is to write the Lewis structure. Be very careful to be sure to include all of your lone pairs. You then count up the number of electron domains around the central atom. That will define your electron domain geometry. And then count how many of those domains are bonding versus non-bonding, which will then give you your molecular geometry. Remember that double and triple bonds count as one electron domain for determining molecular shape. We'll note here that lone pairs actually take up more space than bonding pairs, and so they tend to compress the angles a little bit. To illustrate this, we'll take a look at the three different molecular geometries that we find within the tetrahedral electron domain geometries. For example, methane, CH4, has a tetrahedral electron geometry and a tetrahedral molecular geometry with tetrahedral bond angles of 109.5 degrees. If we have ammonia, however, NH3, with an electron domain geometry still of tetrahedral, however, this lone pair here takes up more space than the bonding pairs do. And so that's going to compress these angles in just a little bit. And so that will actually lead to bond angles that are a little bit less than 109.5. If we go to a bent conformation, that compresses our bond angles even more. And so something like water, H2O, has two sets of lone pairs on the oxygen molecule. And so that's going to compress these bond angles even more. And so we get bond angles that are even less than we would see with ammonia. And we can see that illustrated here with much better drawings than what I just did. And so we can see our classic 109.5 bond angles with methane. Our trigonal pyramidal bond angles, slightly less. We get 107.5 due to the compression from our one lone pair. And then to the bent conformation of water, we now have two lone pairs on our central atom, which compresses our bond angle even more, down to 104.5. And so now try an example. Go ahead and stop the video now and draw the structure of phosphorus pentachloride. And then restart the video to check your answer. And so we see here the Lewis structure of phosphorus pentachloride. And so we now want to determine the actual electron domain and molecular geometries of this compound. And so we start by counting up our electron domains. 1, 2, 3, 4, 5. All 5 of those are bonding domains. There are no lone pair domains. And so that gives us our trigonal bipyramidal electron domain and molecular geometry. And so what we want to do next is be able to draw that in 3 dimensions. And so we're going to start with our phosphorus here in the middle. Now remember, with our trigonal bipyramidal geometry, we've got axial and equatorial positions. So the way we are going to represent those are by having 3 of our chlorines in the same plane as phosphorus. 1 chlorine is drawn with a wedge, meaning it is coming at us. And then 1 more chlorine drawn with a dash, meaning it is going away from us. And so now we're going to do the same thing for the PCl4 plus ion. So go ahead and stop the video now, draw your Lewis structure, and then restart the video to check your answer. And so here's our Lewis structure for PCl+. We see that we have 4 electron domain geometries. All 4 of those are bonding. And so we have an electron geometry of tetrahedral and a molecular domain geometry that is also tetrahedral. To draw that in 4 dimensions, we're going to have our phosphorus in the middle, 2 chlorines in the same plane as phosphorus, 1 drawn as a wedge coming at us, and another drawn as a dash going away from us. And now we've got PCl6 minus. So again, stop the video, draw the Lewis structure, restart the video to check your answer. And so here's our Lewis structure. 6 electron domains, all of them bonding, for an octahedral electron domain geometry and molecular geometry. And so now we're going to go ahead and draw that in 3 dimensions. Again, our phosphorus in the center. We're going to have 2 Cls within the plane, and then we'll draw 2 coming off as wedges, and then 2 as dashes signifying going away from us. And so then we can see our axial and also our equatorial positions. And so now we're going to attempt to draw the Lewis structure of that. Now we'll take a look at xenon tetrafluoride. Stop the video now and draw the structure. Restart the video to check your answer. So here we have our Lewis structure of xenon tetrafluoride. We see that we've got 6 electron domains, but 2 of those are lone pairs, meaning we have an electron domain geometry of octahedral, but a molecular geometry now of square planar. And so we would have a couple different ways that we could write the molecule in 3D. We have our xenon central. We could either represent all 4 of the fluorines as being in the same plane with straight lines. And in that case, then the lone pairs would be one coming at us and one going away. We could also represent it like this. And in this case, the lone pairs would be in the same plane as your screen, with 2 fluorines going back behind the screen and 2 fluorines coming at you. This chart here summarizes all of the different electron domain and molecular geometries. If we have 2 electron domains, we have a linear electron domain geometry and also a linear molecular geometry. With 3 electron domains, we have a trigonoplanar electron geometry with trigonoplanar and bent molecular geometries. With 4 electron domains, we have an electron geometry of tetrahedral and molecular geometries of tetrahedral, trigonopyramidal, or bent. If we have 5 electron domains, we have an electron geometry of trigonal bipyramidal, leading us to trigonal bipyramidal, seesaw, T-shaped, or linear molecular geometries. Finally, with a 6th electron domain, we have an octahedral electron geometry, giving rise to octahedral, square pyramidal, or square planar molecular geometries. And all of the respective bond angles are shown too, with examples in our right-hand column. You will receive this chart on quizzes and exams, with the exception of the example column. All other information will be provided to you. You will simply have to know how to use the chart in order to determine the electron domain and molecular geometries. So in this video, we've gone over the theory of Vsepr and how we use the electron domains and the number of bonding and non-bonding pairs to determine our electron geometry and our molecular geometry. I hope this has been helpful. Be sure to come see me if you want some extra help in using the chart and figuring out the geometry of molecules.